Hi, everybody. So now we're going to start a discussion of a really important technique called principal component analysis, which is a way to take very complicated data that possibly has many features and many samples and try to find features which capture as much information as possible in as few features as you can possibly arrange. So the idea here is that you have data which may exist in a very high dimensional space. I mean, in some genomics experiments, you might have a data matrix which has, let's say, 100,000 samples. Each sample is a cell. And for each cell, you might have 30,000 features, which would be the expression level of a particular gene. And trying to make sense of data which lives in of 100,000 vectors, each of which lives in a 30,000 dimensional space, is a very mind-boggling thing to think about. And principal component analysis is the first of many techniques for trying to reduce the number of features that you have to look at in order to still get meaningful information about your data. So let's just remember the general setup that we have. We're given some data in the form of a data matrix, X, which has n rows. Each row is a sample, and k columns, each of which is a feature. And so each column of the matrix represents the measurements of a particular feature of the data for all the samples. As I said, typically these numbers could be quite large. I mean, a row might correspond to a customer, and the column might correspond, the features might correspond to all kinds of demographic information about that customer. Or the rows might correspond to cells, and the columns might correspond to expression levels of particular genes in a cell. And what we're going to talk about is a way to cut down the number of columns that we have to look at so that we can maybe visualize something to do with the data. So let me first of all remind everybody about the sort of two really fundamental measures that you can make of a feature. The first is its mean or average value. So it's if we have a column of our data matrix x1 down to xn, then the mean is just the average value. And we've seen this before. And the variance of a column of the matrix is gotten by taking the average of the squared distance from the values to the mean. So it's the sum of the xi's, that would be the values in a particular column. I haven't listed the index k, which would tell us which column it was. So it's just one of the columns, minus the mean squared divided by n. And we've seen this quite a bit too. This, in some ways, we mentioned maybe is can be thought of as the mean squared error in some settings. And we have a geometric interpretation of this as well, because we can, if we think of our data, of a column of our data matrix as being a vector in n-dimensional space, and we let E be the vector 1, 1, 1, 1, 1, 1, 1, then sigma x squared, the variance, is 1 over n times the distance between the squared distance between the vector x and the vector mu x e. And so we also have a geometric interpretation of the variance. And I'm calling this the sample variance to distinguish it from the variance that we talked about in the probability section. If we had an underlying statistical model and our data was drawn from a probability distribution, then that probability distribution would have a variance. The variance of the data that I'm describing here would be only an estimate of the underlying variance. So that's why it gets the label, the sample variance. These x1 up to xn are just particular samples out of a universe of possibilities. and we're going to take the variance of that sample. I may not always say sample, and so in the context where we're dealing with specific measurements, and I say variance, I mean the sample variance. We're not making any assumptions here about an underlying probability distribution. Okay, now for something new. Suppose that we look at two different feature vectors. If you like, you could think of these as x and y as two different columns in our big data matrix. So we have n rows, and we might have the column x, which say corresponds to the weight of the car, and y, which corresponds to the engine displacement. Or in the genomics case, x might correspond to one gene and y might correspond to another gene, and the numbers are the expression levels. The covariance, which is a measure of the relationship of these two features, is gotten by taking the sum of the products of the differences between the x's and their mean and the y's and their mean, and then dividing by n. So if you want to think about this in geometric terms, you can think of the vector x, which is x1 down to xn, and y, which is y1 down to yn. And what you're doing here is you're taking x minus mu xe, and you're taking its dot product with y minus mu ye, and you're dividing that by n. So in some sense, if the variance is the norm of a vector, then the covariance is the dot product of two vectors. Now, one issue with the dot product is that it's sort of unscaled. And one thing if we know about the dot product of two vectors is that the absolute value of A dotted with B is the norm of A times the norm of B times the cosine of theta. And this value here, the cosine of theta, doesn't depend on the lengths of the two vectors. It only depends on the angle between them. And in our geometric setting, we can compute this angle, the cosine of the angle, by thinking about our geometric situation. Remember that sigma xy is 1 over n times the dot product of our feature vector x minus mu x times our feature vector y minus mu y. Sigma xx squared is 1 over n times the norm of x minus mu x squared. Sigma yy squared is 1 over n times the norm of y minus mu y. I should put the e in here. Squared. And so this number that I'm calling rxy can be thought of as the dot product of x minus mu x times y minus mu y e divided by the norm of x minus mu x e y minus mu y e. In other words, if here we have the vector x minus mu x, and here we have the vector y minus mu y, rxy is the cosine of the angle in between. And I don't need this absolute value here, provided that we sort of understand what we mean by the cosine of an angle in terms of its sine. So what these vectors are in a high dimensional space, but they span a plane, and in that plane it makes sense to talk about the angle between them, and that's what this cosine does. And to give you a sense about what this measures, I've taken here and plotted 3 different data sets. So each of these data sets, there's a collection of points x1 up to xn and y1 up to yn. And I've made a scatter plot of them under 3 different circumstances. This data set has an R value between it of 0.8. So the angle between x minus mu x and y minus mu y, the cosine of that angle is 0.8. And as you can see, there is a relationship between x and y. As x increases, y increases, and the values of y and the values of x are somehow close together. In fact, there's a strong sense that you have a linear relationship between x and y, which goes like this. In the middle here, I've drawn a case where r equals 0.4. Now the cosine of the angle is smaller, so the vectors x and y point in somewhat different directions. And you can see that what that tells you here is that there's still a linear relationship, but it's not as strong, or at least an apparent linear relationship, but it's not as strong. X and y vary more independently of one another. And if there were no relationship, if r were closer to 0, then these points would just kind of form a circle, and knowing the value of x would tell you nothing about the value of y and so forth. And the sign of r also matters, because in this example, I've drawn a picture where r is minus 0.8. And now you can see the same relationship that you saw in the case where r is equal to 0.8, but sort of in the other direction. Here, increasing x decreases y. Here, increasing x increases y. So the correlation coefficient, which is what this Rxy is called, or the correlation, the sample correlation value, is a measure of how related, or one measure of how related the features x and y are. And of course, in the most degenerate case, which is where the correlation is 1, that means that the angle between x and y is 0, and that means that the two features point in the same direction, so they're linearly dependent. And as we know, that has then they're redundant, and so there's no need to use both of them. But even if the r is very close to 1, it's telling you that the two features have a lot of the same information in them. Okay, now we can relate this back to something that arose in our study of linear regression, and that's the covariance matrix. So if you recall, in the calculations involving linear regression, the matrix D0 arose 1 over n x0 transpose x0, where x0 is the centered data matrix. It's the data matrix that the columns of x0 have mean 0. And you remember the way we made that was to take x0, and we took the subtract is x, but subtract the average of each column. From that column. And this is the matrix which arose in linear regression. And if we divide, at least x0 transpose x0 was. And if we divide this d0 by n, this is called the covariance matrix. And the reason it's called that is because it summarizes all of the variances and covariances of the data that we're interested in. And so to see exactly what's going on, let's think for a moment about what happens when you multiply x0 transpose times x0. So x0 looks like, here's x0. It has the first feature here, and I'm just going to use the fact that we've already done the centering, so that the mean of each column is already 0. So in the calculations where I have to look at x minus mu xe, I don't have to do that anymore because the means are 0. And we have k features. Each column here is the measurements of a given feature. So there, if we're looking at a weight loss study, all of those numbers are the weights of all the participants in the study. When we multiply x0 transpose times x0, we have to replace, we have to take x0 and turn it on its side. So its first row, x0 transpose, its first row goes x11, x21 out to xn1. And its last column is x1k out to xnk, and it's k by n. And when we multiply x0 transpose times x0, we get to practice our matrix multiplication yet again. We're going to take the first row of x0 transpose, which is here, and multiply it times the first column of x0. And what we get here is going to be x11 squared plus x21 squared. In other words, we're going to get here the sum of j1 squared as j goes from 1 to n. And in the other diagonal entries, so for instance, in this diagonal entry, in the second, so maybe I'll just make a note here that make a note here that d11 is going to be 1 over n, because so d11 is the diagonal entry, dii are the diagonal entries of d0. So d11 is 1 over n sum xj1 squared. J goes from 1 to n. And more generally, the ith diagonal entry is j equals 1 to n of ji squared. Because when you take the ith diagonal entry, you're going to take the ith row of x0 transpose, which is the ith column of x0, and you're going to take the dot product of those two things. And remember that since these numbers have mean 0, these are exactly the variances, sigma squared, of the ith column of the original data. And the off-diagonal entries, dij, is going to be the ith column of x0 dotted with the jth column of x0 divided by n. And that's the covariance of the ith and j columns. And this is why D0 is called the covariance matrix. The entries of D0 are the variances of each column on the diagonal, and it's a symmetric matrix where the off-diagonal entries are the covariances. So the 2-3 entry is the covariance of the second column with the third column. And similarly, the 3-2 entry is the covariance of the second column with the third column. So the covariance matrix contains all the information about the relationships between the columns of the data matrix, at least as far as that can be detected through the use of variances and covariances. And just to sort of show you how you can visualize such a thing, this is an example of what's called a density grid plot. And what we have here are 50 points in R2. So our data matrix, X0, is 50 by 2. 50 samples, 2 columns corresponding to X and Y. And the way we visualize the covariance matrix is we have a 2 by 2 matrix here, which is what, so D0 in this case is 2 by 2. And its entries are the variances of X and the covariances of xy. And the way we make sense of this is we plot for the diagonal entries, and it's sort of twisted around. So this would correspond to, this is a histogram here of x against x. So it shows how often each value of x occurs. The height of the bar is how many values of x occur with that value. And the spread in this histogram tells you something about the variance of x. And the spread in this histogram tells you something about the variance in y. So that's the sense in which this is a visualization of the variances. And these two plots are actually the same, except that x and y are reversed, and they show the covariance of x and y in the sense that, as we saw before with regard to the correlation coefficient, they show you that, that as x increases, y increases. And also as y increases, x increases. So it gives you a sense that the covariance is positive in these cases. Now, a graph like this can only tell you so much. I mean, if you had 15 features, you would end up with a 15 by 15 grid of these things. And personally, I find them hard to make sense out of. But for 2 variables, this is maybe a nice way, and maybe even 3 variables. This is a nice way to see the relationships between any pair of the individual features. So that's our discussion of the covariance matrix, and we're going to be using the covariance matrix a lot. So we're going to get quite familiar with it in the next few lectures as we talk about principal component analysis.